my screen?
Hi, thank you everyone. Now we have our speaker, Dr. Papri Dey. Please go ahead and.
Yeah. Hello everyone. Thanks to the organizers for the invitation. And yeah, I hope you can see my screen, right?
Yeah. Yes.
So today, welcome to my talk, first of all. The title of my talk is Real Degeneracy Loci of Matrices and Their Configurations. And this talk is based on an ongoing project with Dan Edidin. So briefly outline is as follows. First, I will define the problem and give you one motivation behind this problem. And in this talk, mainly I will talk about configuration of degeneracy locus of 4 linear operators in R3 and its connection with Kelly symmetroid. And at the end, I will show how to generalize this idea for m+1 linear operators in Rm. This is the slide to show my gratitudes towards this computer algebra systems. Because in algebraic geometry, people frequently come across these 3 questions. Does the polynomial system have solutions? Are they real or rational? What is the dimension of the solution set? Can we express them explicitly? So these algebraic software systems or computer algebra systems can be used to certify their answers to these questions. And definitely in this project, mainly I have used Maculae 2, Mathematica, and Singular. So here is our problem. So consider a collection of linear operators, R linear operators in Rm. We define the degeneracy locus of this scripted A, collection of linear operators in Rm, denoted as X. X is the set of points such that rank of this matrix is less or equal to m-1. The problem of degeneracy locus, looking at the degeneracy locus of collection of matrices or linear operators, is motivated by some results in phase retrieval. What is phase retrieval? In our topic, actually, we want to define generalized phase retrieval. The generalized phase retrieval is the problem to recover a vector x in Rm up to sign from a given measurement, which is quadratic measurements, x transpose Aix dot 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 x transpose Arx, for a given collection A equal to A1 to Ar. Now, this collection A, scripted A, has the phase retrieval property if the map is map MA, which is defined from Rm modulo plus minus 1 to RR, is injective. In 2019, Wang and Zhu, they have proved that this map MA is injective at some point X if and only if the vector span Rm for a collection of symmetric matrices AI. This result equivalently can be restated as this way. The collection of symmetric matrices does not admit phase retrieval if and only if our degeneracy locus contains a real point. Okay. And it is proved also that for any generic collection of R linear operators, when R is greater or equal to 2m-1, the collection has phase retrieval property. And if m equal to 2 to the power k plus 1, then R equal to 2m minus 2 collection of linear operators. And if you look at the degeneracy locus, it will always have 2 real points. That means you don't have, the collection doesn't have phase retrieval property. So our aim is to determine conditions on a collection of 2m minus 2 real matrices, which ensure that the degeneracy locus is entirely real. And that degeneracy locus we call as real degeneracy locus and abbreviated as RDL. And at this point, I hope that I could convince you one importance of this result or looking at this problem. So in our first interesting case in this setup, when we have m equal to 3 and r equal to 4. M equal to 3, which is of this form, and r equal to 4, 2m minus 2. So from their result, it is already known that if you have 4 linear operators in R3, you cannot get that collection doesn't have phase retrieval property. Now we are interested to find conditions on the matrices AIs to A4, A1 to A1, A2, A3, A4, such that we'll get this some idea about this degeneracy locus. What do I mean by idea? Like geometric configuration, dimension of this degeneracy locus, and many more stuff. So this locus is the point of is the set of points for which this rank of this matrix is less or equal to 2. So if we look at any general collection of A1 to A4 in R3, we have shown that this X is the set of a 0-dimensional subscheme of degree 6 in P2. In simpler version, it is a 0-dimensional projective variety of 6 points. Okay. Now, the outline of the proof is as follows. If we look at the locus of rank 2 3x4 matrices, that is a 9-dimensional subscheme in P11. And for a very specific choice of A1 to A4, if they are generic choice, most of the cases we will get 2-dimensional linear subspace. I mean A1x to A4x. For generic choice of A1 to A4, it will span a 2-dimensional subspace in P11. Now it will intersect this determinantal variety with the linear subspace, 2-dimensional linear subspace. In generic situation, we'll get a 0-dimensional subscheme. And that's why we are getting a 0-dimensional. And if we use the degree formula for determinantal variety, then we can get the degree 6 here. Now, our aim is to determine conditions on these matrices AI such that we'll get all 6 points rational points. Moreover, we'll have explicit expression or formula to get these 6 points in the degeneracy locus. And that can be done if we can find or express them as a rational function of the entries of matrices. So here is our setup. Look at the variety X1 of 4 tuple of 3x3 matrices, which is sitting inside P35, such that all AI are in the linear span of 4 fixed rank 1 matrices. Here, so first you choose 4 rank 1 matrices and then construct your matrix AI such that AIs would be in the linear span of 4 fixed rank 1 matrices. Then we have shown that for generic matrices A1 to A4, which satisfies this condition 1, this specific choice, Then the degeneracy locus X consists of 6 rational points, the thing we want, we desire. And they can be obtained by intersecting the 4 projective lines in P2. And here is the idea behind the proof. Since EI is a rank 1 matrix, so kernel of EI, that is a 2-dimensional subspace in R3, equivalently a line in P2. So when we do intersect 2 generic line, we'll get point. Now for any pair ij, one more thing, please interrupt me anytime because I may not be able to see the chat. So please feel free to interrupt me anytime. If you have any question or anything, please do that. So what I was saying, now it will intersect 2 lines, then generically we can expect that we get a point. So now here, for any pair of ij, if we take the intersection of kernel of EI with kernel of EJ, we can expect generically we will get a point in P2. And these points, if you look at this intersected point, common points, these points has very specific structure. If we will add this A1 to A4 on these points, we'll get these vectors, and then they always lie in 2-dimensional subspace. And this 2-dimensional subspace is spanned by the images of EK and EL, where K and L is the complementary set of I and J. Degeneracy locus, so we can say that it's the union of these points, Xij, which correspond to the pairwise intersection of 4 lines. Now we have explicit expression to describe the degeneracy locus in this setup. Here is one example. If you look at 4 lines, x equal to 0, y equal to 0, z equal to 0, and x plus y plus z equal to 0, then we do have the normal vectors associated with these lines are E1, E2, E3, E4. Now, image of EI that is spanned by these vectors, then degeneracy locus X is nothing but taking cross product of these vectors E1, E2, E3, E4. And 4 choose 2 gives you 6 points. Another important thing to notice is that these points are not in general position. They do have special configurations. Because if you look at x1 2 point, 1 minus 1 0, x1 3, 1 0 minus 1, and x1 4, they are collinear. Similarly, you have 3 more triple, which forms triad. Now, quadrilateral in incidence geometry, this is known as quadrilateral configuration. If you have 6 points and 4 triples with collinear condition, which is shown in this picture, like P12, P13 point and P14, they are collinear here, and P14, P24, and P2, you can see 4 triples are there. And in dual projective space, we have 4 lines in a plane, no 3 of which are collinear. That gives us quadrangle configuration, which is shown in this figure. And nice fact about it, it's very easy way to see this one is like, this is something like this configuration when you have this condition where P is the number of points, L is the number of lines, and gamma is the number of lines per point, and pi is the number of points per line. So if you look at the picture now, 6, 2, 4, 3, it means you have 6 points, 4 lines. We do have 6 points, which are P1, 2, P1, 2, P1, 3, P1, 4, P2, 3, and this 6 points, 4 lines. And in each, you have 2 lines per point. So P1, 2, if you look at, then you see that 2 lines are intersecting at P1, 2. And in this picture, it's just dual 4, 3, 6, 2. You have 4 lines and 4 points. I'm sorry, 4 points, which are these points, and 6 lines. Our P1, 2 line, they have become here points. I'm sorry, other way. Points here in the picture 1 has become, yeah, they have become lights. Okay, and we see that in each per point, you have 3 lines intersecting, and per line, we have 2 points. If you look at P1, 4, you have 2 points. So this is nice configuration, already exists in the literature, and we have used this fact to study our degeneracy locus. So here I would also like to mention that our method doesn't assume AI so far, AI to be symmetric matrices, but one can definitely choose AI to be symmetric matrices. In that case, we need to choose EI as the rank 1 symmetric matrices. And now natural question arises that, is this the unique way to get 6 rational points for symmetric or non-symmetric case? So answer to this question is not yet known to us, but we can answer to this question partially in the sense that if we have 6 rational points with quadrilateral configuration, then we can definitely answer to this question. And converse turns out to be true. Like if you have 6 rational points with quadrilateral configuration, then they will always come through this setup. X1, which is a variety of 4 linear operators in R3, and they are in the span of 4 fixed rank 1 matrices. So here is the recipe to prove that statement converse. So we can translate our situation into a rational map in this form. Like we do have a rational map from A36 to this Hilbert space P26, and here, wait. So what happened to my pen? It's not working anyway. So Hilbert space, yeah, we do have map this rational map, and we also observe that this rational map commutes with the action of the general linear group. So as we have also seen, I think due to time constraint, I didn't focus on that fact that we do have nice property about quadrilateral configuration. One of them is that it is, if you consider the set of all order 6 tuple points, and then consider the group action GL3 on that set, GL3 acts transitively on the set S. That means it will have exactly 1 orbit. And that facts allow us to move from one point to other point in the degeneracy locus. And that's why when we are trying to prove the converse, it is sufficient to prove that fact for a very specific choice of degeneracy locus. And that's why we are going to choose this, our favorite degeneracy locus, as a running example. Now observe that the phi inverse fiber of this map consists, we want to prove that this fiber consists of 4 tuples of matrices which lie in the linear span of 4 fixed rank 1 matrices. In order to do that, we use dimension counting. So we one side, we have already shown that this variety has dimension 24 if we have imposed this condition that AI have fixed null spaces, which is equivalent to the fact that it is related to one specific degeneracy locus. Okay. And on the other side, we could prove that this dimension of fiber of this map is a rational variety of dimension 24. So we can conclude that our desired thing, if we start with a degeneracy locus of 6 points, which has quadrilateral configuration, then we'll get the matrices which are in the linear span of 4 fixed rank 1 matrices. Okay, and this is some technical issue I will skip for this talk. So here is another nice, what's the time? How I'm doing with the time? Okay, so as my son is waiting, I'm a little bit worried. So this is another side of story is that this degeneracy locus has nice connection with Cayley symmetroid. Now, what is Cayley symmetroid and why it is true? First, it is based on one fact that any 4 tuple of symmetric matrices is in the linear span of 4 fixed rank 1 symmetric matrices. And this can be also proved using dimension. Oh, I'm sorry. I'm using dimension counting. It would be both sides. It would be like 24 dimension of the locus of matrices, symmetric matrices, which are in the linear span of 4 fixed rank 1 matrices. That is 24, and we can see that immediately because one symmetric matrix is locus of symmetric matrix of 3 by 3 symmetric matrix is isomorphic to A6. So 4 tuple, we have actually that locus of 4 tuple 3 by 3 symmetric matrices that is isomorphic to A24. So both way its dimension, they do have same dimension. Now, what is Cayley symmetroid? How they are related to Cayley symmetroid? A 3-dimensional symmetroid of degree D, known as Cayley symmetroid. It's a surface with defining function f. F is a determinantal, where defining function is a determinantal polynomial. So Cayley symmetroid of degree D is a surface in P3 where the defining equation f is determinantal. And a symmetroid is real if all of its coefficients of this polynomial are real. And it's very real if AI can be chosen to be real symmetric. So the variety of Cayley cubic symmetroids is actually irreducible and has codimension 4 in P19. Codimension 4. And this also can be easily seen, but maybe I'll skip this part for this talk. So now we'll see how symmetric matrices are related to very real cubic symmetroid in this setup. So if we have this matrix A1x to A4x, that can be expressed as a linear matrix polynomial of size 3 by 4, which is L. That means our degeneracy locus is nothing but the set of points where rank of this linear matrix polynomial is less or equal to 2. And look at this identity. This is actually a consequence of Hilbert-Burch theorem. We can see that this matrix has 3 by 4, here 4 by 1, and here U is 3 by 3 matrix, and it's a 3 by 1. And look at this determinantal polynomial. If we'll take this matrix and determinant of this linear matrix polynomial, then it gives the Cayley symmetroid. And equation 2 also shows that this Cayley symmetroid has 4 nodes, which we have seen here as 4-dimension 4. And these 4 nodes also can be obtained from the degeneracy locus. And that is shown in next example. So our running example shows us that this is our standard degeneracy locus for the line, 4 lines this. Then the corresponding Kelly symmetroid is this one, which we can see in next slide actually. We can visualize here. And these are the 4 nodes or singularity, which can be obtained from the degeneracy locus or loci, these points. And this is these are the points, singularity locus for this polynomial. And here another fact is that other side of story, if we blow up of P2 on these 6 real points, then we'll also get another Kelly symmetroid, Kelly qubit symmetroid, which is shown here. And singularity locus of this one is as follows. Now, upshot is that singularity loci of the very real Kelly symmetroids is determined by the linear combination of Aij, where Aij is this linear combination of rank 1 matrices. And here, yeah, maybe I'll stop here. I'll not go through this generalization part. Thank you. Thank you for your attention.
Thank you so much for the talk.
You're welcome. It's my